All right, so here is objectives 6 and 7 on your objective sheet. All right, we're going to be talking about a closed system here and what happens in a closed system. So the first thing we got to talk about is we got to talk about Newton's third law. All right, um, and that is every force has a partner, and if you remember, they're equal and opposite, and those forces act on different objects. So Newton's third law isn't going away. It's still a very large part of what we're going to do here. So um, that's we got to make sure we remember what Newton's third law is. When we have an interaction that is comprised of only uh, partner forces, so only third law forces, we call that system. And remember, this would be two objects, so the system would comprise two objects here, a closed system. And so a closed system has no outside forces. It's only the partner forces from whatever interaction is happening. And then the thing with closed system is that momentum is conserved. Now I'm going to show you what that means here in just a second. All right. But we're going to be talking about how these forces uh, produce a closed system. So let's say we have like object A right here, okay, and object A is moving this way, okay, and let's go ahead and label that object A. All right, so there's object B, A, and then we have object B that's over here, and we'll say object B is a little bigger, sure, why not? All right, and we'll say that it's object B, and we're going to say that object B is moving that way. Now, what's going to happen? These two things are going to collide, right? They're going to hit. They're going to have an interaction. And so A is going to hit B, and B is going to hit A. And according to Newton's third law, those two forces will be the same. So this would be a closed system. There's no other forces. Now, we can ignore the normal force and gravity in this situation. Why? Because normal force and gravity go vertical, right? Normal force and gravity are vertical, but this is happening in the horizontal direction, so they are not in the same direction, and so they have no bearing here. They won't play. Okay, so what this means, all right. So what Newton's third law tells us is that the force of A on B is going to be equal to the force of B on A, but in opposite directions, which means that the one of them has to be negative. So that means the force of A is going to be equal to the negative force of B. Now, how does this apply to momentum? Well, if you think about it, during that collision there, during that interaction, it's going to happen at the same time for both objects, right? Object A is going to hit B at the same time B hits A. So it's going to happen at the same time. It's going to take the same amount of time. So that means that the force of A times the time it takes is equal to the negative force of B times the time it takes. And T is the same for both. So immediately you should see, okay, that means the impulse of A is equal to the negative impulse acting on B. Okay, well, we can take it a step further, all right? Because you remember, impulse is change of momentum. So that means that the final momentum of A minus the initial momentum of A is equal to the negative final momentum of B minus the initial momentum of B. All right. So if I kind of rearrange all of this here, and I'm just going to move down a little bit so I have a little bit more room. So like so. All right. What I'm going to do here is, remember, this is the A side, so final minus initial equals, and now I'm just going to manipulate that through, and what I get is initial minus final. over here. All right, that's an F. This is supposed to be an F right there. That just came out really bad. All right. So what I can do then is if I rearrange this equation, I add my initial momentum of A over to the other side, add my initial momentum, and then add my final momentum, add my final momentum. Now remember, this is of object A, this is of object A, this is of object B. All right. We get the final momentum of object A plus the final momentum of object B is equal to the initial momentum of object A plus the initial momentum of object B. That's a B. All right. So what we end up with is this really nice equation, all right here, that illustrates what happens during a closed system. And what it says is the total momentum initially in the system, so object A and object B, when you add them together, it equals the total momentum after the interaction of A plus B. So that means the initial momentum equals the final momentum. All right. So what we really, on your equation sheet, what will end up happening is it ends up looking like this, is like total momentum, the initial momentum of the system equals the final momentum. And then what you're supposed to do is be able to work it out to, okay, so initial of A plus initial of B equals final of A plus final of B. Okay. Now, the reason we take this general form and not this general form on the equation sheet, even though this is on the equation sheet right here, is because there's different situations in which a closed situation can occur. So if we come back up here, there are three scenarios that make up, that are that happen from a closed system. All right. So scenario one is the explosion or recoil. So that's scenario number one. So now scenario number one, what it shows, and I'm just erasing some of this over here so I have some room to write. So what we get here is we get two objects that are together. All right, and those are together, and they're touching, and initially they're not moving. All right, and so then what happens is after the explosion or the recoil, excuse me, is that object A will move off in this direction and object B will move off in this direction. Okay. And so what ends up happening, we just use the equation I just showed you. Initial momentum equals final momentum. We just know that the initial momentum of the system is zero. So that means the final momentum of the system is zero. That doesn't mean that A and B each have zero momentum. That means when you add A's momentum to B's momentum, you get zero. Okay. And what you get here is this scenario here. So typical examples of this would be shooting a gun. And this is where the recoil comes in, because the gun has recoil. It bounces back. So the bullet goes one way, the gun pops back the other way. If you've ever shot a rifle or a shotgun, you know that the gun will actually hit you in the shoulder pretty hard. That's the recoil, and that is because of conservation of momentum. The bullet must go out with a certain momentum. That means the gun has to go back with that same momentum. Other examples would be like a child standing in a wagon and then jumping out of the wagon, right? The wagon goes one way, the child goes the other way. Another example would be, um, two ice skaters on a frictionless ice surface that push apart away from each other, right? Or even a hockey player on ice skates who hits a hockey puck and the hockey puck goes one way and he goes the other way. But those are just some general examples, and those are going to be situations where two things start together. Like I said, an explosion or some recoil event happens, and they move away from each other afterwards. Scenario two that's going to happen is the inelastic collision. Now, inelastic really means that kinetic energy is not conserved. For our purposes in momentum here, and we'll discuss that definition later, is really that it is something like this, is where you have object A, you have object B, right? They're moving independently of each other. So a couple of things can happen here. They can be moving the same direction. They can be moving towards each other in opposite directions. It really doesn't matter. But what ends up happening is after they collide, so they're apart initially, but after they collide, they stick together. All right. And then they move as a single object is what this is. So common examples of this, a tackle in football. You have two people running independently, and the defender tackles the offensive player, wraps up, they move as one unit. Car accidents where the cars become entangled and they move together. So these are all examples of inelastic collisions. All right. And then the last type would be an elastic collision. All right. An elastic collision is one where kinetic energy is conserved. Again, that is not what we're going to define it as for now. It's very similar to an inelastic, where inelastic, it sticks together. Elastic just means they're going to separate. So after they hit and collide, they will each move off on their own separate ways. So examples of this would be probably a football tackle that your coach wouldn't be too happy with. That's where you just like lower your shoulder and try to run into somebody and you hit and bounce off of them and don't wrap up. Another example would be like pool balls are probably the best example here. Billiards is the best example. Like you hit the cue ball into the one ball, two ball, whatever. They don't stick together after they collide. They both kind of move off on their own. So that is an elastic collision, and kind of what you would see there. Okay. You could imagine a few other scenarios there. So now what you can do here is with all of these situations, you can start working on those chapter 9 problems. And the other day I told you could do 1 through 3. Well, with these equations, you should be able to start taking on the rest. All right. And the equation you'll need is basically this. Now, what this is not on the quiz tomorrow. And I'm going to go over it in detail more when I'm gone. But if you have some time and you have some energy, go ahead and start taking on questions 4 and on that worksheet. And like I said, it'll be this equation here that you'll need to use